Thank you for the introduction. I have no disclosure to make. So today I will first briefly review the kinetic model of ASL signal, and then I will describe the different labeling techniques with the spatially selective ASL and velocity selective ASL respectively. When using a RTO bolus for perfusion measurement, perfusion-weighted signal is proportional to a convolution of an RTO input function with an impulse response function, under the assumption that this is a linear time-invariant system. And the CBF here is only a scalar of this convolution. So for DIC PWI, we will measure the RTO input function from a large vessel, and then the tissue concentration curve. And then through a deconvolution, we can estimate CBF and the impulse response function. But for ASL, we are limited by a much lower ISMR. So we only have time to measure one data point at this entire kinetic curve. So we have to assume that the RTO input function, which we happen to be able to control nicely, that is the RTO input function with a delayed RTO transit time, and then the impulse response function at the simple exponential decay with blood T1. Then we can calculate the CBF. Spatially selective labeling typically apply the labeling pulses and then label the blood before it enters the brain. Pulsed ASL labels all the blood through a thick slab in the neck region with the leading edge and the trailing edge, and which have different RTO transit times. So the RTO input function will have a further decay at the trailing edge. And continuous ASL labels the blood through a thin slice at the carotid and the vertebral artery. And so it's a step function, and normally has a much longer bolus duration. But as we can see that the spatially selective labeling is sensitive to RTO transit time. So we have to acquire the post-labeling delay longer than the RTO transit time. To minimize the sensitivity to RTO transit time, velocity selective labeling was proposed that labels all the blood in the brain. So the leading edge of this bolus is very close to the tissue, and the trailing has a long bolus duration, and the trailing edge will have a signal decay. So if you look at the kinetic curves, the peak amplitude of this kinetic curve is around the blood T1 value. So you just need to acquire the data before it reaches the maximum signal. Pulsed ASL has many different techniques with different configurations for label and control modules. Continuous ASL has simple continuous RF and gradient waveforms, but it's challenging for the hardware systems. So PCASL, pseudo-continuous ASL PCASL was proposed that applied pulsed RF and gradient fields and allow it to be implemented on modern clinical scanners. So about 2 years ago, there was this ASL white paper that recognized that the high ISMR of PCASL and also the ability to be implemented on human scanners, it was adopted as a preferred method for clinical applications of ASL. In this paper, a detailed description of the parameters for labeling, acquisition, and quantification were provided for standardized protocols across vendors. I think currently all three large vendors have provided PCASL with this kind of parameters as product sequence. So we have to recognize the limitations of this PCASL sequence. In addition to the sensitivity of the arterial transit time with generally spatially selective ASL, PCASL itself, we know that the labeling efficiency is sensitive to the flow velocity through large neck arteries. And also, labeling efficiency is sensitive to B0 and B1 field homogeneity around the neck arteries. So to reduce these sensitivities, David Aesop's group very recently made a study to optimize their labeling schemes. And so in their study, they suggested that it's better to use an unbalanced PCASL. And the labeling location should be around L2, which is above the carotid bifurcation and below the V3 segment and between the second and third vertebrae. And they also recommended specific B1 values and average maximum gradients, which are different than the ASL white paper that accomplishes much better robustness for velocity and B0, B1 homogeneities. So here in this image, you can see the much better tolerance for the off residence. Dr. Han-Zhang Lu's group recently also conducted a study on the cardiac cycle effect. And they found that the cardiac triggered PCASL can actually improve the temporal stability compared to the standard non-triggered PCASL sequence. You can see that quantitatively, by doing cardiac triggering, they can reduce the coefficient of variation by 50 to 60% for parenchyma tissues and large vessels. So to take into account of the arterial transit time effect, Danny Wang's group proposed a multi-delay, multi-parametric ASL, which in their specific protocols, they implemented 4 delays with a simple quantification model to estimate arterial transit time, CBF, and arterial CBV concurrently. And they studied on patients with acute ischemic stroke and compared with DIC PWI and showed reasonable correlations between their parameters and the parameters from the DIC. Another way to obtain the ATT information is through the time-encoded ASL. So standard PCASL, you do a labeling for like almost 2 seconds, and then you wait another 2 seconds before the acquisition. So to take advantage of the time that you are waiting, Matthias Van Asch's group developed this protocol that insert a lot of small label control modules with a Hadamard encoded matrix. And then in their quantification, the standard PCASL module can still give you the CBF maps. But they use this additional time-encoded matrix data to obtain the ATT maps. And this actually does not cost any temporal SNR sacrifice. So they call this a free lunch approach. The third method that was recently developed from Han-Zhang Lu's group was the ASL methods based on the principle of fingerprinting. They have a randomized order of the label and the control They also randomize the duration of the labeling modules, and then they use a dictionary to extract the information and estimate multiple parameters at the same time, with CBF, the bolus arrival time, CBV, and plus the B1, T1 information. So velocity selective ASL, typically similar to PCASL, they have a VS labeling module, and then a labeling delay and the background suppression. But it's to reduce a contribution of the venous blood, which is accelerating after the labeling. They applied this sequence need to apply a bipolar question gradients for both label and control modules to only measure the signal that under the cutoff velocity, so that only the arterial blood that is decelerating is being quantified as perfusion. So there's two velocity selective modules. Conventional velocity selective sequence is starts with a 90-degree hard pulse, and then a pair of adiabatic refocusing pulses surrounded by bipolar gradients to encode the velocity information, and then it will be tipped back by a 90-degree pulse. So the phase modulation on the transverse plane will generate a quasi modulation of the velocity on the Z magnetization at the end of this pulse stream. When you assume a laminar flow through the large vessels, then you integrate through the cross section, you will actually get the sink function, where above the cutoff velocity, the blood signal is dephased, and then the tissue signal within this cutoff velocity will be maintained. If you turn off these gradients or have a unipolar direction to have a compensated waveform, then all the signals are maintained. So the difference is the blood signal. So there was a few clinical studies demonstrating the utilities of this velocity selective ASL. This is one of the few conducted by a Stanford group, where they compared the velocity selective ASL with 5 different labeling delays of PCASL and a CT study, perfusion CT. And then they show that when you have long transit time delays because the patients are with moya-moya disease, then the shorter labeling delays will be have underestimate the CBF. But you can see this effect is diminished when it's at a much longer delay. But the velocity selective ASL seem to show that it's less affected by the long transit time. Another very recent clinical applications is on placenta perfusion. This group from National Children's Hospital compared velocity selective ASL with a PCASL, which were labeled at 2 different locations, and show that significant improvement of the signal by the velocity selective ASL was actually the PCASL labeling only achieved 16 or 9% with these 2 different labeling locations, the perfusion signal compared to the velocity selective ASL. This is because that at the body, placenta area, the flow velocity B0, B1 environment is much worse than the neck regions. So there are some further optimization of this from the conventional velocity selective saturation pulses. And one of the main constraints of the velocity selective ASL is the gradient effect. So Eric Wang's group and a group from Oxford developed a pulse train called symmetric Burr-8 pulse, and demonstrate that this pulse has a much better robustness to gradient effects compared to a Burr-4 pulse. A Burr-4 pulse should be better than the hard pulse used in the very original pulse streams. And then they compared the symmetric Burr-8 pulse with different pulse streams using velocity-selective ASL pulse streams like this dual refocused hyperbolic secant pulse and Burr-4 pulse and asymmetric Burr-8 pulse, and compare with the pulsed ASL P-core as a reference. You can see that with the first 4 velocity-selective ASL labeling, you can see some overestimation or asymmetry left and right, and you see much less of that effect of the symmetric Burr-8, which is largely because the effect of the gradient effect artifacts. So, because the conventional velocity-selective pulse train is saturation-based, then in order to improve the velocity-selective ASL, the ISMRM of the velocity-selective ASL, Edgar group proposed a skin to have multiple VS saturation pulses before the acquisition. So here they demonstrate that if you apply another velocity-selective saturation pulse after the first one, then you can actually increase the dynamic range of the labeling signal. So this is an example of their skins, comparing the traditional 1 VSS module and 2 VSS modules. They found a higher signal. They actually quantified as about 22% increase of the average SNR. So our group recently developed a Fourier transform-based velocity-selective inversion pulse train, which in theory it can double the SNR than the velocity-selective saturation pulse streams. So it's actually the next 2 or 3 slides I will break down this pulse train to make it simpler for audience to understand. For the Fourier transform based excitation is already long been recognized in the spatially selective excitation pulse, where you have a 1-dimensional sync pulse, then there you can get a selective slice selection. And the gradients is actually encoding the K-space through this the RF pulse. And then the velocity selective excitation, the concept of this velocity selective excitation was proposed that digitize this sync RF train and using the bipolar gradients to encode the velocity K-space. There you can get a thin kind of a velocity selective profile, but with aliasing sideband because of the small number of digitization. So this is the original, very original skin of velocity selective pulse train that have multiple velocity encoding segments followed by bipolar gradients. But this module is, this skin is sensitive to off resonance because the phase generated by the velocity cannot be differentiated from the phase generated by the B0. So if you have a B0 effect, then you can see that the velocity selective profile will be shifted along the B0 off resonance. So we know that we need to add refocusing pulses. The first skin was adding a single composite refocusing pulse per step. And then this was done in a Stanford group for peripheral MRA application on 1.5 Tesla. They demonstrated that the velocity selective profile got improved for ±80 Hertz. Our group added a paired refocusing pulses, and also with the phase cycling, which actually can much further improve the velocity selective profiles up to ±200 Hertz that enabled us to do the applications on 3T at brain. But we want to recognize the effect of to the B1 here, that it's still, this saturation band is still sensitive to the B1 effect because we are using the hard pulses to encode the velocity selective profiles. So we demonstrate that this velocity selective saturation pulse, this Fourier transform-based velocity saturation pulse train can be very nicely demonstrating its effect on all the large vessels inside the brain. So for the perfusion, we need to really be careful with gradient artifacts. So we optimize our protocol and then compare it with the conventional VSS pulse train and show this similar performance. Then we conduct our study on 8 healthy subjects, compared our VSI methods with conventional VSS pulse train and PCASL. So you can see that we did a 2D single-shot EPI for 5 slices and repeated 30 times. And we calculate the temporal ISNR. We see that our VSI methods can have 40% higher ISNR than the conventional VSS, and it's only 9% lower than the PCASL. And the reason we didn't reach the 100% higher theoretical gain of ISNR is because the labeling efficiency of our VSI pulse train is still sensitive to the B1 effect, and also because it's relatively long, like 50 milliseconds, it still has a T2 effect and some other temporal velocity change effect. So Matthias Van Arsch group also changed the conventional velocity selective module from using a bipolar gradients to a module using unipolar gradients that can actually achieve the acceleration selective modules. That the velocity selective modules only use the first gradient moment, and the acceleration selective modules utilize the second gradient moment. And they compared acceleration selective ASL with PCASL, with VS-ASL with or without crushing gradients right before the acquisition. And they show that the acceleration selective ASL also have a higher ISNR in the tissue compared to the conventional VS-ASL and PCASL. But it has much less of the signal from the venous blood because this module itself can only label the arterial blood, doesn't need a second module to remove the venous blood contribution. So they also did a nice study on healthy volunteers, comparing all these different velocity selective, acceleration selective methods with PCASL and reference with the PET data, and they show that velocity selective and acceleration selective ASL both provide similar CBF signal distribution qualitatively and similar CBF maps quantitatively compared to the O15 PET. So in summary, spatially selective ASL, the pulse ASL has a relatively lower ISNR. PCASL definitely has an advantage of higher ISNR, but they are sensitive to transit delays. And there are methods developed to take into account the transit time information using either multi-delay or time-encoded or fingerprint ASL. The velocity selective ASL has minimum sensitivity to transit time delays, but needs careful configuration to minimize gradient-related artifacts. The conventional velocity selective saturation-based VS-ASL has lower ISNR. And to increase ISNR, there are also different approaches already in place to give the like multi-VSS modules and acceleration selective or Fourier transform-based VS inversion-based VS-ASLs. Thank you for your attention.